Hello, my name is Nabila Balqis Binti Hassani and we are from Group 17. I will tell the introduction of our integrated project. So, Chemica is a company with a major expansion plan to produce a purified terephthalic acid for their own use and to satisfy the local demand. So, there are two steps to produce a purified TPA, which is the first one, step 1, oxidation of pyroxylene to produce solid crude TA, and the step 2 is hydrogenation of crude TA to produce purified TA. So in this task, in this integrated project, we are required to do the step 2, which is the hydrogenation of crude TA to produce purified TA. There are several questions that are given by the Chemica to produce purified TA.
Today I will explain to all of you about the type of reactor and catalyst used in this integrated project. This is question 1. So firstly, our team have read some of the journals and they have suggested some of the catalysts. Okay, one of it is palladium and carbon and palladium and tin. So in our team, we want to suggest that palladium and tin is the most efficient than palladium and activated carbon. Okay, why? Because as for the because if you synthesis by both cooperation and successive iteration method. Okay, this catalyst is a solid catalyst. So you want to use PBR, which is a type of reactor that use a solid catalyst.
So for the reactor separator system, first we use the packet bed reactor, which includes a catalyst that is heterogeneous for the solution that will increase the surface area of the reaction and also will increase the velocity and the rate of the reaction to occur. And this will lead to the favorable formation of PTA. Next, we will use an evaporator, which occurs at the boiling point of the reaction, and the reaction will become more concentrated because most of the water will be removed from the solution. And then we will follow to the crystallizer that is operated by cooling the reaction remaining, and the terephthalic acid will be separated from the mother liquor that contains the impurities from the reaction.
There are many strategies to maximize yield and purity of TPA, which is number 1, the addition of carbon dioxide in the BX oxidation to TPA instead of traditional air oxidation system, which increases the yield and purity of TPA while significantly reducing the solvent burning. Next one is another alternative catalyst in order to resolve the environmental and equipment corrosion problems using a cobalt zirconium catalyst system. The third one is another promising alternative to carry out the reaction of PX oxidation to TPA other than acetic acid, which resulted to 90% of yields. The fourth one is Osada and Savage found that adding oxygen in quick, discrete, small influence on the cost of PX partial oxidation reaction, resulting in over the 90% of yields. The last one, which is reactor is configured to disperse the liquid phase in its ice-fine droplets, should favor the production of TPA product with higher purity and yield.
So for the sizing of reactor, we will choose reactor of packed bed reactor. So we need to do assumptions of steady state reaction and its first order, no volume expansion, no pressure drops, no radial concentration, and also catalyst decay are neglected. After assuming all these assumptions, we will also assume for the FA0 will be 30,000 tons per year, as in the integrated projects of task it is given, and stirring rate is 1000 rate per minute, Ca0 will be 0.025 mole, and X will equals to 90.5% based on the journal from Langley 2013. And after that, we will use the formula for volume for PBR, packed bed reactor, which is dFA over dW equals to RA, and we'll do all the derivation for formula deduction, and we get the last formula will be W equals to V0 over K bracket ln 1 over 1 minus X.
For the calculation part, 2800 parts per million will be equals to 2800 milligram per dm cube. And we use this value to put into the formula, and we get Ca0 equals to 0.0187 m. And after that, we use the formula of Fa0 equals to Ca0 V0, and we can calculate our V0 will be equal to 3415.508 dm cube per hour. After that, according to the journals, we use the K average by dividing 4 K values into 4, and we get 19.78975 per minute, and we transfer it into hours, which is 1187.385 per hour. Using the density of 1630 G per dm cube, we can use our formula W equals to rho V0 over K ln 1 over 1 minus X to find the weight, which is 11036.703 gram. And then finally, using the formula of W equals to rho V, we can find the volume, which is equals to 6.771 dm cube for the sizing of PBR packed bed reactor. For the stoichiometric table, there will be chemicals of C8H8O3, H2, H2O, C8H8O2, TA, H2O, which is the inert gases, and also the total. All of this is categorized into chemicals, and there are columns for symbol, initial, change, and remaining. For the symbol, we use A, B, C, D, I, and H. For the initial, C8H8O3, also known as symbol A, will be categorized as Fa0, and whereas for B will be 2FaO, as delta B is 2 over 1 according to the equation, which is A plus 2B. For C and D, the initial will be 0, as these are the products. And whereas for the change, A and B will get negative change as they are the reactants, and for C and D, the change will be Fa0x. And whereas the last remaining column will be initial plus change. Then after that, there's the F total, Ft equals to Ft0 plus Fa0.
Hi, me again, Omar. So now I will be explaining about the type of separation system used to produce purified TA in crystal form. So in our integrated project, so we have some process. One of it is oxidation, the other one is hydrogenation. So at the end of the product, we have mixing or mixer of this solution. So how we want to separate all of this mixing? The first one is you use evaporation. So basically evaporation is occur between 140 Celsius to 200 Celsius. So we want to evaporate the P-silene in this mixing. So when we evaporate, we will get the crystal form in the first method. And then the second method is crystallization, which is occur also in this reactor. So the temperature is between 140 Celsius to 200. So whether we want to lower the temperature and also we want to reduce pressure. So at the end of the product, we can see that there are some crystal formed at the end of the reactor.
The three above mixtures is then transferred from the bottom of first slurry tank to a first dissolver tank. The content in the first dissolver tank is then heated indirectly from 130 degrees Celsius to 180 degrees Celsius. The batch content in the crude crystallizer is then reduced in pressure in the manner described above with concurrent removal of flash, solvent, and cool from 180 Celsius to 50 Celsius by an external cooler to generate desired supersaturation for TA crystal to grow. At the conclusion of first crystallization part, the slurry is dropped into a third holding tank and transferred into a second filter tank, which is the crystallization part where it is filtered at a continuous rate.
For the second crystallization part, NMP is used to wash solid in the second filter. The washed solid is dropped into the second dissolver tank where it mixes with NMP to form supersaturated feed, and NMP is heated from 45 degrees Celsius to 180 degrees Celsius, is fed to the second dissolver tank. The solid is initially washed with NMP at 45 degrees Celsius to displace the remaining mother liquor from the solid, and then the solid is washed with the low boiling displacement solvent, such as water, to displace NMP from the solid and sent to a vacuum dryer. After that, the slurry from the wash column is fed to the soaker, where the temperature is around 150 degrees Celsius to 200 degrees Celsius to to remove trapped solvent from the crystals. The slurry is finally filtered and dropped to a product dryer where water in the solid is removed by heating and purging with a counter-current flow of heated nitrogen. And the dried PTA product is removed from dryer and is stored in, lastly, the product bin.
So to maximize the production of PTA in powder form, first we need to control the quality of the crystals, which is also controlled by the crystal size distribution. The crystal size distribution is directly affected by the non-equilibrium state of the system by the supersaturation. So in cooling crystallization, the supersaturation is created by the decrease in temperature, and the products depend on how the solution is cooled. So the best method would be to cool the solution linearly with the help of a thermostat, which ensures that the supersaturation rate is highest in the beginning of the process, because the stable solid particles, which are the crystals, can only be formed when the supersaturation rate is high enough.
According to the task given, crude terephthalic acid contains 4-carboxyl benzaldehyde, Ta, which stands for terephthalic acid, and also PTA, which stands for paratolic acid. Crude terephthalic acid and water is mixed together in a mixing reactor where hydrogenation part occurs, and after that it flows into the evaporator where evaporation occurs and water vapor is evaporated. After that, the slurry stream will flow in the crystallizer where crystallization part occurs, and the last product, final product, which is purified terephthalic acid, is formed in the crystal form.
So I will tell the reflection for this integrated project. So description for this integrated project, we were assigned by the Chemica to propose of ways to produce purified terephthalic acid, and the feelings for our integrated project is that we feel the hardship and challenges to do this project, but this is a quite interesting experience for us. And evaluation, the good experience for this project is we get to know our learning outcomes throughout the semester for these two subjects, reaction engineering and separation process. And analysis for this subject is for reaction engineering part, we use packed bed reactor and PDSN FMWCNT as a catalyst. And there's two steps, oxidation and hydrogenation. And for separation process part, we for the separation process part, we use two separators, which is the evaporator and the crystallizer. And there's some ways that we found to improve the crystal formation and to maximize the production of purified TA in the crystal form. So conclusion for our integrated project is that we learn more details for the subject, for example like the reactor, the separator such as crystallizer and separation process performance. So we hope that we can apply this knowledge in our daily life and also at workplace during internship or during work life in future. Thank you, and that's all from us.